So let's talk about the global carbon cycle. Again, what you've got when you model a nutrient cycle is you've got a group of reservoirs that are connected by fluxes. And there are a handful of major reservoirs that I want you to know about in the carbon cycle, and a few minor ones that I don't expect you to know about. The major reservoirs that you should be aware of are here. One thing that is going to be true in all of the nutrient cycles is that some reservoirs are a whole lot bigger than others. So for example, living organisms down here, basically you're talking about 615 billion tons of carbon in them. In the atmosphere, there's only 750 billion tons. I think it's billion rather than trillion. I'm going to be really embarrassed if I got this wrong, but I'm just going to go ahead and keep saying billion because it's late and I've got to finish this video. The soil and soil biota, that is, organisms living in the soil, contains a couple thousand billion tons, but the biggest reservoirs of carbon in the world are the oceans and sedimentary rock. Now, the form of carbon that you find in these different areas is different. Obviously, in living organisms, carbon is the most important element. Carbon is found in energy-containing compounds as well as things like amino acids, which make up proteins, our nucleic acids, structural compounds like cellulose, and so on. They're all carbon-based compounds. In the air, carbon is found mostly in carbon dioxide molecules, and that's also true in the water. Water has an amazing capacity to dissolve, to hold dissolved carbon dioxide, and accordingly, this is a huge reservoir for carbon on Earth. And it's maybe the most important of the reservoirs that you need to keep in mind. Sedimentary rock is a much, much bigger reservoir of carbon. There's a truly gigantic amount of carbon stored down there, but as it turns out, it's not all that important for the cycling of carbon on the time scale that we're really interested in. So here are your reservoirs. What about some of the details within some of these reservoirs? Well, I'm not going to go into too much detail about this, but you know essentially how a food web works. You've got producers that are taking up, in this case, the carbon dioxide. They make their bodies largely out of carbon atoms. Some of those carbon atoms get eaten by consumers. Some of them get passed to decomposers. When respiration takes place, those carbon atoms can be released into the water and make their way from there into the atmosphere in the form of carbon dioxide. What are the rates at which carbon atoms are moving around in this whole scheme? So gross primary production is the accumulation, or is related to the accumulation of biomass by producers. And on Earth, this happens at about 120 billion tons every year. 120 billion tons of carbon is taken out of the atmosphere every year and locked up in the bodies of living plants. When consumers eat those land plants, or when the land plants burn energy, respiration happens. And respiration by consumers and the plants put together returns essentially all of that carbon to the atmosphere on net. Obviously, the same thing is happening for aquatic ecosystems. You've got uptake of carbon by producers as they burn energy, and as consumers and decomposers burn the energy that was stored up by producers, that carbon goes back to being carbon dioxide again. So there's a cycle that goes through the living ecosystems. They both cycle with respect to the carbon dioxide that's found around them. There's also a very important flux that is going back and forth between the atmosphere and the water. This is basically diffusion. Most of the Earth is covered with water, and where that water comes in contact with air, carbon dioxide molecules can move freely back and forth between the two. If the concentration of carbon dioxide uh, increases in the atmosphere, you're going to see net diffusion into the water. If the concentration in the water is too high, some of that carbon dioxide will escape into the atmosphere. So diffusion can move both directions, although generally the two fluxes, the flux into the water and the flux back out, are pretty close to being equal. There is an asymmetry here, which we'll talk about in just a minute. From the land plants and the consumers, carbon does make its way down into the soil by rotting. But then basically the same amount that goes down into the soil pops back up again as organisms decompose that dead matter and as those soil organisms go through their own energy use, resulting in respiration. There are a few minor fluxes here that you don't really need to worry too much about. Every year, a little teensy bit of carbon gets buried irretrievably at the floor of the ocean. It's on its way to becoming rock and will never be seen again as far as most organisms are concerned, at least not on anything less than a very geologic timescale. There is a small flow of carbon in the form of decayed organic matter that is carried from land into the oceans every year. Rocks get worn down, and that releases a little bit of carbon into the ocean, but it's a very small amount. And finally, volcanoes sometimes shoot some of this carbon that's been locked up in rock back into the atmosphere. But again, these are very mild fluxes. These are very small. The ones that you really need to know about are things like diffusion, respiration, photosynthesis. Oh wait, there's one more. This is a reservoir which we're increasingly concerned about, the fossil fuel reservoir. This is a modest-sized reservoir. There's a lot of carbon locked up in that relative to, say, the amount of carbon that's locked up in the organisms that are still alive today. There have been a lot more dead organisms in Earth's history than there have living ones, and that's reflected in the size of this reservoir. As human beings have taken this fossil matter, these dead organisms, out of the ground and set them on fire, the carbon that is in their bodies, their ex-bodies, I should say, is released into the atmosphere as carbon dioxide. This is a new flux. This is a flux that human beings have invented, and it has changed the entire nature of the global carbon cycle. If you look at the size of this flux, about 9.1 billion tons of carbon moving from this reservoir here into this reservoir every year. This is a small number. It's an order of magnitude smaller than all of these other fluxes. It's 1/75th of the amount of carbon that is currently in the atmosphere. But it is substantial enough to make a really big change. Because if this happens year after year after year after year, pretty soon you're starting to build up way more carbon dioxide in the atmosphere than you originally had. Okay, so you should pay attention to the size of these fluxes. Okay, what's happening is that we are pumping a tremendous amount of carbon dioxide into the atmosphere because of the use of fossil fuels, and a lot of it is staying there. Our bacon is actually being saved by a couple of different processes right now. Because we're cranking up the concentration of carbon dioxide in the atmosphere, some of it is diffusing into the oceans, which fortunately are tremendously large and can store a huge amount of carbon dioxide. The other thing that we're doing by pumping carbon dioxide into the atmosphere is we are fertilizing plants. A higher concentration of carbon dioxide in the atmosphere allows plants to go through photosynthesis more efficiently, more rapidly. And so actually these numbers should not be equal. There are a couple billion tons of carbon that are going They're taking the trip from the atmosphere to the plants each year and not going back up. In other words, the net uptake of carbon by the world's plants is greater than the amount that's being re-released from living communities. This is a big deal. You've only got a couple billion tons being pulled out every year by the oceans. You've got a couple billion tons of carbon dioxide being pulled out of the atmosphere every year and locked up in plants. But together, that's about half of the amount of carbon dioxide that we're putting into the atmosphere every year. Global climate change, which is caused by high concentrations of carbon dioxide in the atmosphere, would be twice as bad today if it weren't for the oceans and the plants pulling carbon dioxide out of the atmosphere and putting it somewhere where it doesn't change the world's temperature. Another thing that human beings are doing is that we're changing the amount of plant matter that is available on the planet Earth. Human beings plant new plants, but they mostly cut down older ones. And the net effect of this is to remove the biomass that is here in the form of plants. That biomass has to go someplace. And so one thing that happens when a forest gets cleared is that the carbon that was locked up in these trees gets released into the atmosphere as carbon dioxide. That happens if the trees are burned, but it also happens if they rot. Their carbon ends up heading up into the atmosphere regardless. Because there are fewer plants, the uptake of carbon dioxide by the world's plants is also slower than it could have been otherwise. So this is another way in which human activity is indirectly increasing the concentration of carbon dioxide in the atmosphere by interfering with the plant community that would otherwise be taking it up. Why does all this matter? Well, I imagine that you've heard this story, but I'm going to go over it very quickly in case you haven't. Sunlight comes in from the sun to the earth in a very broad array of wavelengths. There is infrared, there is visible light, there is ultraviolet, and there are wavelengths on either side of that that we're not going to worry about right now. But they're coming in a broad variety of wavelengths, and they make their way down through the atmosphere. Now, there are a lot of components, molecules in the atmosphere that block certain kinds of radiation. Okay, so some of the gases in the atmosphere are very effective at blocking particular wavelengths. But a lot of the ultraviolet and visible light that is coming down through the atmosphere clearly makes it to the surface of the Earth. If it didn't, you wouldn't be able to see anything, and you certainly wouldn't get a suntan. The problem is that when that energy strikes the surface of the Earth, it can be absorbed and then re-radiated at a different wavelength. In particular, what happens is when visible light and ultraviolet hit the ground and are absorbed by the ground, say they heat up things like rocks or water or trees or what have you, and then they're re-released in the form of heat. That energy is re-released in the form of heat or infrared radiation. Unfortunately, one of the chemical compounds that is better at blocking infrared radiation than it is at blocking other spectrums, other wavelengths of light, is carbon dioxide. So the energy from the sun passes straight through carbon dioxide on the way down because it's in, say, the visible light spectrum, but then cannot pass back up out of the Earth's atmosphere because once it is re-radiated, it is at the wavelength of infrared radiation. In a nutshell, carbon dioxide traps infrared radiation close to the Earth's surface. And well, infrared radiation is heat. That is what is causing the world to warm slowly up. This has been happening for quite some time. If you look at the amount of atmospheric carbon dioxide that we have Today, we're actually well past this graph by now. But you can see back in the 1960s, there were only 315 parts per million of the atmosphere were carbon dioxide. In only 40 years, we've gone up from about 315 to 380 parts per million. And it has, believe me, continued to rise ever since this. This is a really big change in the concentration of a component of the atmosphere. It might seem as though the sky is limitless, but it actually does not have room to simply swallow all of the carbon dioxide that we are pumping into it. By introducing this new flux into the carbon cycle, we're changing the size of the atmospheric reservoir for carbon dioxide, and that in turn threatens to change basically everything else on the planet Earth.